Let's tackle this core problem right out of the gate. Why the invisible noise? Well, to understand how this happens, we need to look past the surface of your CAD tools. The truth is, a schematic only tells half the story. It assumes ground is this magical, zero-ohm, perfect sink. But out there in physical reality, your ground paths, the actual copper traces, the vias, the wires, those are what completely dictate whether your product passes or fails regulatory compliance. Unwanted voltage drops across these physical conductors create common-mode ground potentials. And what does that do? It turns your cables into highly efficient, totally accidental antennas. Henry Ott dedicated his definitive book on electromagnetic compatibility using this exact quote from Albert Einstein. Everything should be made as simple as possible, but no simpler. And honestly, he hit the nail on the head. When we oversimplify our grounding systems, when we assume a single line on a drawing is a perfect zero-volt reference everywhere, we are literally inviting catastrophic high-frequency noise. We absolutely have to treat ground as a physical, dynamic component of the circuit.
Moving on to Section 2, Atomic Ground Topologies. To really build that dynamic understanding, let's zoom in. We're going from the macro-level circuit board right down to the fundamental atomic behavior of signal grounds at different frequencies. Now, if you memorize only one engineering rule today, make it this: the 100 kHz threshold. We essentially have two main approaches here. First, single-point grounds. These are expertly suited for low-frequency applications, mostly from DC up to about 100 kHz. They prevent low-frequency ground loops by forcing currents down specific isolated paths. But what happens when we cross that 100 kHz line? Multi-point grounds become absolutely mandatory. Let's look at how this builds out in practice.
Take a look at this setup. This perfectly illustrates a multi-point ground system. Notice how multiple circuits drop straight down to a shared, solid ground plane. The absolute critical element here is keeping that connection length to a bare minimum. In a multi-point system, your connections from the circuit to the plane must be as short as humanly possible, usually just a tiny fraction of an inch. Why? Because we're desperately trying to minimize the impedance when routing down to that low impedance ground plane.
Let's use a vivid visual analogy to make this concrete. Think of ground impedance exactly like a water pipe. At low frequencies, your ground path acts like a wide, clear, totally open water pipe. The water, or the current in this case, just flows easily. But at high frequencies, parasitic inductance kicks in. It acts like a stiff, heavy valve suddenly slamming shut, choking off the flow. Even a perfectly straight piece of wire becomes a massive roadblock for high-frequency current.
Which brings us to Section 3, the math of ground impedance.
To truly understand that choking valve, we need to dive into the math. We're going to treat these foundational equations with absolute rigor so you never have to guess at a ground path again. Look closely at equation 3.1. Z sub G represents our total ground impedance. Mathematically, this is defined as R sub G, which is your standard DC resistance of the copper, plus J times omega times L sub G. That second half, that's the frequency-dependent inductive reactance. And remember, omega is equal to 2 times pi times the frequency. What this equation physically tells us is that as frequency goes up, that omega term absolutely explodes. The source text points out an amazing fact. At frequencies just slightly over 13 kHz, a simple, straight 24-gauge wire sitting 1 inch above a ground plane actually has more inductive reactance than resistance. That's wild.
So let's apply that ground impedance to a working circuit using equation 3-7. VL1 is the voltage across your load in circuit 1. In a perfect world, this would just be VS1, your source voltage. But check out the end of the equation, plus ZG times the sum of current 1 and current 2. Because these two circuits share a physical ground path, the actual voltage across your load is corrupted by that common ground impedance, ZG.
Let's break down that corruption a bit more. That first part, I1 times ZG, represents intra-circuit noise. That's just your own circuit's current reacting with the ground impedance. Annoying, but manageable. The real danger is the red term, I2 times ZG. This is intra-circuit noise. This math proves exactly how current from a totally different circuit, circuit 2, multiplies by that shared ground impedance to inject noise directly into circuit 1. Your beautifully clean analog signal is suddenly polluted by another circuit's behavior simply because they happen to share the same piece of copper.
All right, Section 4, Common Impedance Coupling Walkthrough.
Let's take all this math out of the abstract and apply it to a concrete, real-world example to really lock in your intuition. In this schematic, look at how circuit 1 on the left and circuit 2 on the right have return currents, I1 and I2. They both flow back to the power supply through a shared bottom wire.
Remember, that bottom wire is not 0 ohms. It represents that common line impedance we just talked about, ZG. These two circuits are entirely forced to share that single physical return path.
So if you want to calculate exactly how much noise one circuit is shoving into another, just methodically follow these steps. First, identify that shared ground impedance, ZG. Next, figure out the transient current of circuit 2. Let's say circuit 2 is a digital logic gate that just snapped open, creating a massive current spike. That's your I2. Finally, just multiply that current spike by the shared ground impedance. Boom! That calculated voltage is the exact amplitude of the noise that is mathematically rippling straight into your hypersensitive analog component in circuit 1.
The crucial takeaway here is a very strict engineering rule. High ground impedance, whether that's low-frequency resistance or high-frequency inductance, combined with a large transient ground current, equals a common impedance failure. No way around it. If you have a sensitive, low-noise margin circuit tied to that same ground, you are going to fail EMC compliance. Guaranteed.
Section 5. High-frequency pitfalls and hybrid grounds.
Okay, we've mastered the math. Now it's time to expose the hidden gotcha. This is the exact edge case that trips up even senior PCB designers working with high frequencies. Here, someone meticulously created a single-point ground system, right? They wired everything back to one distinct point to avoid those pesky ground loops. But look at those dashed lines labeled stray capacitance. This is the ultimate trap. At high frequencies, stray parasitic capacitance naturally forms between your circuits and the ground plane. Because capacitive impedance drops as frequency rises, the high-frequency current literally ignores your long, inductive single-point ground wires. It takes the path of least impedance right through the stray capacitance. It magically transforms your perfectly designed single-point ground into an unintentional, heavily radiating multi-point ground loop. It's crazy.
So what's the fix when a system is dealing with both low and high frequencies? Enter the hybrid ground. Think of a hybrid ground like a frequency-selective toll booth. If a car is driving slow, say a low-frequency DC current, the toll booth blocking arm is down, so it acts just like a single-point ground. But if a high-speed ambulance comes flying through, representing high-frequency RF noise, that toll booth arm flings wide open. It suddenly acts as a multi-point ground to let those fast signals pass straight to the ground plane. This is absolutely essential for wideband signals, like video, which span from 30 Hz all the way up to tens of megahertz.
Let's look at the two flavors of this. On the left, we've got a capacitive hybrid ground. By sticking capacitors between the circuit and ground, we create a really high impedance at low frequencies, so it's effectively a single-point ground. But at high frequencies, those capacitors become low-impedance short circuits, safely dumping the RF noise to ground. On the right side, we have the exact inverse, an inductive hybrid ground. Here, inductors pass your low-frequency 50 or 60 Hz safety currents without breaking a sweat, but they firmly block high-frequency noise from radiating out over your power cables.
Finally, Section 6. Essential EMC grounding takeaways.
We've covered a tremendous amount of ground today, pun totally intended. Let's do a rapid-fire recap of the 3 critical engineering rules we've pulled from this explainer. Rule number 1, single-point grounds are strictly for low frequencies, under 100 kHz. Rule number 2, multi-point ground planes are absolutely the only way to conquer that massive high-frequency inductance that tries to choke your return currents. And rule number 3, ground is never 0 ohms. Ground impedance, ZG, always dictates your signal integrity. Knowing exactly when to switch your topology at that 100 kHz line and deeply respecting equation 3-1 is your ultimate key to passing EMC testing. I'm going to leave you with a provocative question to ponder the next time you're reviewing your boards. Is your meticulously designed low-frequency ground inadvertently acting as a high-frequency antenna because of stray capacitance and unseen inductance? Go check your board layouts and keep equation 3-1 in your head while you do it. If you found this breakdown valuable, make sure to hit subscribe for more EMC and automotive communication protocol survival guides. Keep learning, keep designing, and we'll see you in the next explainer.